Okay, real quick review of where we left off. We're in chapter 12. We're talking about radiation properties like reflectivity, transmissivity, absorptivity, emissivity. And we did an energy balance on the incoming radiation on the surface. And it led us to the equation. By the way, these guys are all dimensionless. They're all between 0 and 1. But when you add up the reflectivity, the absorptivity, and the transmissivity, you should get 1 for a surface. If you see the key word opaque surface, that means thermal radiation does not get through, so tau is 0. Black surface, emissivity 1. A diffuse surface, we talked about that last time. There's diffuse irradiation, there's diffuse emission of a surface. That just means, in this case, here's the emission from a surface. The emission is not a function of direction or the angle theta. Or the incoming radiation is uniform over the surface. It's not a function of the direction that it comes from. That's a diffuse surface. Just to go through the capital letters, capital E, emissive power of a surface. The energy per time leaving a surface as a function of the surface temperature and the emissivity. Irradiation, what comes into a surface from all the surroundings. This might be this might not be in your notes yet. Radiosity, capital J, is how much energy is leaving the surface. E is the emitted. Plus, there'll be some reflection from the incoming irradiation. So what leaves the surface? Emitted plus reflected. Okay, now, we talk about a black body. Is there a way to get something close to a black body in a laboratory environment? Yes, there is. It's on figure 1211. You can look at that. Figure 1211, it's up on the board here. But in case you need to refer to it, that's where you find it. This is a model of a large enclosure. The enclosure walls are kept at a temperature T. Forget the middle one, just forget the middle part. There's emission from the walls in the enclosure. It bounces off the walls. It's reflected. It's absorbed. It bounces around here. If you have a small opening in that enclosure, what leaves that small opening appears to have come from a black body at the temperature of the walls T. That's one way you can approach a black body experimentally, maybe in a physics lab. Okay. A large object, heat the walls, put a small hole in the wall. The radiation leaving that small hole has the spectral appearance of black body radiation. Also, if you put a small object in that large enclosure, the incoming radiation G looks like it comes from a black body at the temperature of the walls again. Temperature, not the temperature of the small object, the temperature of the walls, T. Put a dime in a basketball. Okay, that's it. Small object, dime. In a large enclosure, basketball. Okay, that kind of a scenario. Okay, we'll use this in a problem later on. Okay, now, one of the last things in that area of definitions, we've got one more, I think. Let's see what it is. Yeah, here it is. Okay, something called Kirchhoff's laws. Okay, the first one of the Kirchhoff's laws. There's really three, but I'm going to just do two. The third one's not that important for our class, so I'll just do two. You can say that epsilon lambda equal alpha lambda if the surface is diffuse. kind of walks you through it in the chapter. That's the first of Kirchhoff's laws. The second one is you can say epsilon equal alpha, no lambda subscript. Don't forget the lambda subscript means the word spectral. This is the spectral emissivity. This is the spectral absorptivity. Spectral means at a particular wavelength. What's the value of emissivity at a particular wavelength? I'll put a note here. This is spectrum. This is called total. The total emissivity equal the total absorptivity. The total means integrated over all possible wavelengths, 0 to infinity. The total means integrated. You integrate epsilon lambda over all possible wavelengths, lambda equals 0 to lambda equal infinity. That gives you what we call the total emissivity or the total absorptivity. That's true if the surface is gray. There's another qualifier there too. If the incoming radiation appears to have come from the same temperature as the surface, but that happens rarely, so the one we're interested in is this reason. Okay. Opaque surface, black surface. Now we have another one, chapter 12, gray surface. Properties independent of wavelength. Properties independent of wavelength. For instance, here's epsilon lambda versus lambda. Oh, it doesn't depend on wavelength. That is a gray surface. Yeah, that's a gray surface. It might be alpha lambda, looks like this. It might be rho lambda, looks like this. Properties, epsilon, rho, alpha, tau, independent of wavelength. Okay, so Kirchhoff's laws. Okay. I think that's about all we need. Yeah, okay. Let's work a couple problems using what's on the right-hand side of the board. Chapter 12 is difficult to read cover to cover. You're much better off using the notes as a guide and filling in what maybe you need to fill in from the class notes in the chapter. But to read it cover to cover, you won't sleep well at night, okay? Okay. We boxed in equations. We had the displacement law, we had Planck's law, we had the band emission, we had all that. So that was last time. Okay, so here we are this time. We're going to use this now, we're going to use this, and we're going to use this. All right, so let's take a look at problem 1258. It says that we have an opaque diffuse surface. It says we're given spectral absorptivity as a function of wavelength. Okay, spectral absorptivity means alpha sub lambda. The lambda means spectral. As a function of wavelength, lambda. We're going from 0 to 5. 1, 2, 3, 4, 5. From wavelengths of 0 to 2 microns, wavelengths in microns. Alpha lambda is 0.4. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Out to 2. Then it goes up to 0.8. Then it goes out to 5 at 0.8. Then it comes down to 0. And it stays at 0 all the way out. Okay, he says, I'm also going to give you an irradiation graph as a function of wavelength. So he gives a second graph. The second graph is the spectral irradiation, G lambda. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, lambda. From 2 to 10, it's 5,000 watts per square meter. 5,000 watts per square meter. From 2 to 10. Straight line, no. Straight line. Constant out to 10. At 10, drops down to 0 and goes over here. What we'll do the first two parts, three-part problem. First part, what's the total absorptivity of the surface? I'll put it here. Oh, okay. Let's talk about these particular equations. I'm going to add those over here. We're not quite there yet. This is how we find emissivity. Okay, emissivity. How do we define emissivity? Well, let's draw a graph here, similar to something like that. We have we're given the emissive power as a function of wavelength versus lambda. If the surface is black, it looks like this. At a certain temperature, T, a real surface at the same temperature might look like this. Emissive power as a function of wavelength at the same temperature. That real surface is jagged because it's not a nice smooth curve. Okay, it might be this gray paint in the room on the wall. It might be the gray paint. So this would be the real surface. The emissive power of that gray paint here. If we figure out what the black body emissive power would be, it would be this line here. At what temperature? Room temperature, 300 K. Both lines are at, let's just say, 300 K. One's a black body at 300 K. The other one is the real gray paint at 300 K. So if we would take, at any particular wavelength, take and divide the black body, divide the real by the black body, that's a definition of spectral emissivity. So spectral emissivity, epsilon, move it up here, epsilon lambda equal E of the real body, E lambda of T, divided by the black body spectral emissive power. It's just a ratio of those 2 points on a vertical line. Now, if we want to find the total emissivity of the surface, I told you right here, you want to find the total, you integrate over all possible wavelengths, okay? So I integrate these guys over all possible wavelengths. Epsilon lambda, EB lambda, D lambda. This guy right here, just so you know, is epsilon lambda, EB lambda. divided by black body emissive power total. Okay, there it is. Emissivity. Let's do absorptivity. Absorptivity alpha. Same way, we define it the same way. This is the energy, this is absorbed, so it's G absorbed over the incoming radiation G. The absorptivity is defined as the absorbed radiation over the total incoming radiation. Okay, so we define it 0 to infinity wavelengths, alpha lambda, G lambda, D lambda, divided by 0 to infinity of all the incoming radiation, G lambda, D lambda. Okay, that takes care of alpha. Reflectivity. Okay, reflectivity. Rho. Rho is the reflected of the incoming radiation divided by the total incoming radiation. Okay, the last one. Transmitted. Tau. The transmitted incoming radiation divided by the incoming radiation, G. Okay, there are the 4 equations. If you're given a graph of the spectral distribution of any of those 4 properties, epsilon, alpha, rho, or tau, you use these equations then to find the total values of epsilon, alpha, rho, and tau. Let's go back to our problem. What did he give us? Oh, he gave us an alpha graph. Yeah, right down here. I know alpha lambda now as a function of lambda. Good. Okay. Part 1. Find alpha. Part 2. Find emissivity. Okay, let's do part A first. Okay, I'm supposed to find alpha. Well, it's not a big, search. There it is, right there. Got it. There it is, right there. So alpha equal integral 0 to infinity alpha lambda G lambda D lambda divided by 0 to infinity G lambda D lambda Now we're going to integrate by parts. And here's the rule. Every time the behavior changes on either graph, that's going to be your limit of integration. If there's a change in either one of the two graphs, okay. Oh, for the alpha graph, at 2, something dramatic changes. The G graph, yes, at 2, something changes. So my first integral, 0 to 2. What's constant from 0 to 2? Alpha. Pull it outside, the integral sign, 0.4, integral 0 to 2. What stays inside? G lambda, D lambda. The next breakpoint, look at both graphs, 5, 5, okay. Integrate from 2 to 5, okay. What's constant? Look up here, 0.8. Also, G, we'll come back to that. Integral 2 to 5, G lambda, D lambda, plus, 10 something happens, 10, so obviously from 5 to 10 integral, 5 to 10, I'll put it in there, but, well, it's 0. Plus 0, integral from 10 to infinity, G lambda, D lambda, divided by integral 0 to infinity, G lambda, D lambda. Okay. Alpha equal. This is the area under the G lambda lambda graph from 0 to 2. The G lambda lambda graph, 0 to 2. A right triangle, 1/2 base times height. Base is 2, height is 5,000. Plus 0.8 times the area under the G lambda lambda graph from 2 to 5. Rectangle, 3 by 5,000. This guy, 0. This guy, 0. G lambda here, 0. 2 zeros. G lambda 0, alpha lambda 0. Divided by the area under the whole curve. 1/2 base times height. Plus a rectangle, 10 minus 2 is 8. 8 times 5. G equal 45,000. I think that's 14,000. Let me just verify it. Yeah, it's 14,000. So we end up with alpha 0.311. Okay, that's part A. Now we'll do part B. Okay. Find the total emissivity. Okay, total emissivity. Transmissivity, tau, reflectivity, rho, absorptivity, alpha. Oh, there it is. He wants that guy. Okay, epsilon. Epsilon is equal to integral 0 to infinity. Epsilon lambda, EB lambda, D lambda. Okay. Integration. Integration by parts. We're doing integration by parts. That's what we're doing. Anytime there's a change in the epsilon lambda graph or the G graph, that's your limits of integration. Say, yeah, but he didn't give me an epsilon lambda graph. he gave me an alpha lambda graph. I don't have the epsilon lambda graph. Oh, yes, you do. There's a magic word. Diffuse. Go over here. Kirchhoff's laws. Oh, thank you very much. If the surface is diffuse, I can say the spectral emissivity equal the spectral absorptivity. So the graph he gave me for absorptivity is also a graph for emissivity. Okay, there it is. That goes in there. Limits of integration. We've got this, the same thing, 0.4 integral 0 to our 2 EB lambda d lambda 0.8 integral 2 to 10. It's 0.8. Oh, no, sorry, not to 5. 5. 2 to 5. EB lambda d lambda divided by integral 0 to infinity EB lambda d lambda then I say, gee, you know what, this looks familiar. I think I've seen this somewhere before in chapter 12. Yeah, you have. That thing right there is F0 to 2 microns. Okay. Table 12.1. Table 12.1. So this becomes 0.4 F02 plus 0.8 F2 to 5. Band emission. We covered band emission last time, 2 times ago. Okay, got to go to table 12.1 to get the F factors. Lambda 1T, lambda 2T. I need both those guys. Okay, let's read the problem. Okay. The temperature of the surface is 1250 K. All right. At 1250 K. What temperature is that? Well, that's the temperature of the surface, of course. That's 1250 K. So we have 2 microns times 1250 K, 2500. Lambda 2 is 6 times 1250. 5, pardon. $62.50. Okay, we go to table 12.1, and we get F0 to 2, and we get F0 to 5. 162, 757. Okay, there they are. Go back over here, do what it says. 0.4 times F02, 162, plus 0.8. Now don't forget, this is band emission. So you take F05 minus F02. 757 minus 162. And I get epsilon. The total emissivity, 0.540. You can see the answer. The answer is alpha is not equal to epsilon. But of course, alpha lambda equal epsilon lambda. Why? Because of the word diffuse. Go back over here again. When can I say epsilon equal alpha? Here it comes. If I see the magic word, the surface is gray. It's not a function of wavelength. No, it's a function of wavelength. Look at it, it changes. So no, I can't say alpha equal epsilon. Illegal. When did I use the G-graph for the solution? I used the G-graph wherever those equations and boxes show the symbol G. I use the G-graph for this one, and for this one. And where do I use the temperature of the surface? Look, EB lambda, sigma T surface to the fourth, right there. So that's what the G-graph does for you there, okay? It allows you to calculate these properties: reflectivity, transmissivity, absorptivity. Okay, I think that pretty much covers everything on that problem.
Is that supposed to be no alpha
Oh.
is not equal epsilon?
Oh yeah, which one?
On the bottom. Is-
Yeah, thank you. Yes. Thanks. Okay, let's do another one. I'll show you a little variation now. I'm going to put these guys side by side. So I'm going to save this. I'm going to put the next problem right here. 1259.
Professor,
Uh-huh.
how come you don't use the area for the top graph?
Which one? This one?
Yeah.
What area?
When you're doing the calculations, you just use equal to 0.4 instead of like 0.4 times 2.
Don't forget, I pulled the alpha outside. I'm left with what? Am I integrating the area under the epsilon graph or the G graph? This is the integral. This is the area under which graph? I don't have this. I don't have this. No. That's the area under that graph. No, I don't have that. I have this area here. You pull the alpha outside the integral sign, because it's constant. What are you left with? The area under the G graph, not the area under the epsilon graph. Yeah. Okay, let's read this one. Okay, opaque diffuse surface. Well, I'll take this one step further if you want to complete something here. Let's just say somebody also said, find reflectivity. Well, okay. I'm sure not going to go through this thing right here, because I don't have a graph for it. I could get a graph for it, but I don't. But I do know this guy up here. There we go. Alpha. Oh, magic word, opaque. Tau equals 0. Says it over there. Opaque, tau equals 0. So what's the reflectivity? 1 minus alpha. You got it. Okay. So now we found all four properties: epsilon, alpha, rho, and tau. Okay, now we'll do problem 1259. The surface is at 1,000. It's placed in a large room whose temperatures of the walls are 1,500. With an emissivity of 8/10. Okay, find the emissivity, the absorptivity, the radiosity. Let's do the part A first. I'm not going to do part A, I just worked it for this problem. The first part of 1258 said find, well, second part said find emissivity if the surface is at 1250. Same thing here. Find the emissivity if the surface is at 1000. You can do that now. I just worked it for you. The answer is the emissivity is 0.670. C, problem 1258, part B. Okay, you can find it just like we found it. You use the table 12 on the fractions of energy and so on and so forth. So I'm going to draw a picture of what he gave us here, though, and I'm going to put that over here.
You did just say in the problem though that with emissivity of 0.8.
Say it again, sorry.
You wrote with emissivity of 0.8, so why is it 0.6?
Oh, okay. This is a small object in a large room. The emissivity of the walls of the room are 0.8. The emissivity of the small object in the room is 0.67.
Okay.
There's two emissivities,
All right.
a dime and a basketball. What's the emissivity of the inside of the basketball? What's the emissivity of the dime inside the big basketball? Alpha, find alpha. Okay, here's the graph he gives us. He gives us epsilon lambda versus lambda. And let's see, we're given 8/10 up to here. 0.246 microns. Okay, and it goes out to 6 and then down to 0.3. Goes over to 0.6, down to 0.3, and on. Okay, so we're given in this problem an epsilon lambda graph. We use that for part A to find epsilon, just like we did in problem 1258. Over here, what were we given? An epsilon graph. Problem 1259, we're given what? An epsilon lambda graph. What do we do with it? We find the emissivity. We did. We find the emissivity. You can do it. You know the rule. The problem said, oh, it's diffuse. Go over there. If it's diffuse, then that means alpha lambda equal epsilon lambda. So this is the same thing as epsilon lambda graph. Now you go to the equation for alpha. There it is. Alpha is equal to 0 to infinity, alpha lambda, g lambda, d lambda. Now we integrate by parts. Wherever there's a breakpoint in the graph, don't forget now there's only one graph. There's only one graph. There it is. Breakpoint 6. Next breakpoint, infinity. Okay, what's constant? Alpha lambda, 8/10. Pull it outside the integral sign. Okay, next one, from 6 to infinity, alpha, 0.3. Okay, divided by the difference in the two problems. The first problem gave you a graph of spectral irradiation, G lambda versus lambda. The second problem didn't give you a graph, but, there it is. It told you the temperatures of the wall in the room. This problem did not give you the temperatures of a wall in a room. They gave you G lambda versus lambda graphs. They're different approaches to the problems. Okay, let's break it down. I'm going to erase this. We've got this already down. Okay. All right, so that becomes this. Divided by this. Where I replaced the G lambda with an EB lambda. Why can I do that? Well, I saw the magic word. Oh yeah, there it is right there. Large, large. I go over here and say, oh, you know what? This is a small surface in a large enclosure. Yes, it is. And if that's true, you're allowed to replace the incoming spectral irradiation G lambda with EB lambda at the temperature of what? The walls in the room. The walls in the room, not the surface, the walls in the room. I did it. I replaced the G lambda with EB lambda because of that picture over there. Okay, then I say, you know what? I think I've seen this before somewhere in chapter 12. Yes, you have. That's F0 to 2. Okay, so now this becomes 0.8 F0 to 2 plus 0.3 F2 to infinity. Yeah.
6, F0 to 6.
Oh, yeah, it's 6, yeah. On the picture, thank you. This guy was 6, thanks. This should be 6, and that should be 6, and that should be 6. 6, 6, and 6. Got it. By the way, in the book, he helps you. If he means that that G lambda is 0 after 10, he puts a red line in the book. This is a red line, that's a red line, that's a red line, that's a red line, and he puts a big fat red arrow like that, arrowhead. That means assume it's 0 all the way to infinity. When he puts the big fat red arrow here, that means assume that epsilon lambda is 0.3 all the way out to infinity, so you know there's no more breakpoints in it. The big red arrowhead indicates it goes out horizontally to the right until infinity. Okay, table 12.1 again. We have to get lambda 1t and lambda 2t. Well, this guy is infinity. The second lambda is lambda equal infinity. The first lambda is equal to 6. So we have 6 times the temperature. Now you gotta be careful. There are 2 temperatures given here, and don't make a mistake on them. Do you use 1,000 or do you use 1,500? You're saying this is the irradiation. Where did the radiation come from? The walls of the room. Oh, 1,500. Okay, so get the right temperature, and there's 2 choices. The surface temperature or the room wall temperatures. 6 times 1,500, that won't do it. How about 9? All right, so let's do the F's then. F0 to 6 from the table 12.2 is 0.890. F from 6 to infinity is 1 minus 0.89011. All right, so this becomes 8/10, 3/10, so alpha then comes out to be 0.745. Notice from part A, emissivity 0.670. Part B, absorptivity 0.745. They're not equal. Why aren't they equal? Because nobody said the surface is gray. Just like problem 1258. Part C, find J. The radiosity, J. Okay, here it is over here now. What's J? J is the thermal radiation leaving the surface. How does it leave the surface? Number one, it can leave by emission, capital E. Number two, there can be reflection from the incoming irradiation, rho G. Okay, so J equal E plus rho G. All right, so what is E? This is epsilon sigma T to the fourth plus rho. Do I have rho? No. Did it say opaque? Yes, it did. If it's opaque, what do? I put tau equals 0 here, and if I want rho, rho is equal to 1 minus alpha, and I just found alpha. $111,000 watts per square meter. Why did I replace G with sigma T to the fourth? Look at the picture again. For a small object in a large enclosure, G looks like it comes from a black body at the temperature of the walls. A black body, sigma T to the fourth. Well, but you better be careful. This is temperature of the surface, and this is temperature of the surroundings. Don't put the same temperature in for both of you, you'd be dead wrong. There's two different temperatures in this problem. You can see the contrast of these two problems I put on the board. The first problem, somebody can give you a graph of epsilon or alpha or rho or tau. Okay. Then they'll tell you, they'll give you a graph of the incoming irradiation G. They won't tell you the temperature of the surroundings. They won't say it's a small object in a large room. No. This problem, they'll give you again a graph of maybe epsilon, maybe alpha, maybe rho, maybe tau. They'll give you a graph. Here it is. Then they won't give you a graph of the incoming radiation, the spectral irradiation. They'll give you instead the words either a small object or a large room and tell you what the temperature of the walls in the room are. That's when you can replace the G lambda with the EB lambda. Did we ever use this? Nowhere. It's not needed. It's just flag. You don't use that. Because if you read the words below figure 1211, it'll say that this is true irregardless of the emissivity of the walls in the room. This is true irregardless of the emissivity of the walls of the room. It doesn't matter. Change that to 0.1, these answers are still okay. Okay. Oh yeah, chapter 12 is not straightforward. Say, oh yeah, that's really clear, I see that. No, that's not the way it is. Chapter 12 is the toughest chapter in the whole book to read and understand. That's why you want to go by the notes here and then fill in what you want to fill in from the notes with the textbook. But start with a good set of notes. That's the key. Okay, homework is very similar to that. All right, so that pretty much ends chapter 12, and we're going to start chapter 13 on Friday. But I want to go over the homework problem that I passed back and graded. So let me go ahead and put this up on the board here. Okay, I graded the first problem because it was a combination problem of a little bit of analytical work and a little bit of graphical work. So I wanted to see both on a problem. So that problem had both. I'm not going to go over the analytical part. Most people got that right. Find the shape factor from the table, put it in the equation for Q, SK, delta T, bam, that's the answer. But I do want to go through the graphical part because some people had a problem with that. So this is a sphere that's buried in soil, and the temperature of the sphere will assume is T1 on the inside surface of the sphere. I'm going to do a two-dimensional drawing of this 3D picture. I'm just going to assume that T1, just to talk about something, T1 is greater than T2. It would make no difference if I said T2 is greater than T1, but I'm going to say, I'll assume the sphere is hot. It probably is. It's radioactive material. And the soil surface, too, is cooler. T2 is cooler. Okay, draw a heat flux plot. You don't need to draw curvilinear squares. I'm not going to do an analysis for that. Just draw the heat flux plot. Okay. Number one rule, look for lines of both geometric and thermal symmetry. Okay. Only one we got is one that goes right through the center of the sphere. There it is. A line of symmetry. Geometric? Yes. Thermal? Yes. Okay, got it. That line, rule number two, that line is automatically an adiabat, a heat flow line. Yeah, that makes sense, of course. Heat leaves here and goes straight out the top of the soil surface there. Right angle, right angle. Here, this is a heat flow line going straight down. Right angle. The rule set, no, I'm going to draw the heat flow because that makes, I have some intuitive feel for that. But the heat that goes from T1 to T2, I know, rule 3 or 4, it leaves an isothermal surface at right angles. That's the rule. It leaves an isothermal boundary at right angles. And when it gets to the other isothermal boundary, it enters that boundary at right angles. Okay, take the easy one. I think heat leaves here and goes out here. Of course. Leaves here and goes out here. Yeah, sure, there. Okay, keep going. Do the easy one first, though. Okay, it comes out here, it probably goes out there. Yeah, you got it. It leaves here and it probably comes out there. Yeah, you got it. And it leaves here and it might come out over here. Yeah, you're getting it now. All right, there they are. You want to do the whole thing? Don't forget, it's symmetrical. You wouldn't have to, but I'll do the whole thing for you here. Comes out here, goes over here. Okay, there they are. Comes out here, goes way over there. Those are the easy ones. Label them. You see, if you don't label them, I don't want to guess which one's the adiabat and which one's the isotherm. And I've given them something like this on an exam previously. And some people, they didn't label the lines. And I gotta know which ones are the heat flow lines, which ones are the isotherms. So on a problem like this, label the lines for me. Okay. Now we're going to draw the isotherms. Take the easy one first. The first isotherm in this 2D diagram is a circle. There it is. Guess what the next one is? It's almost a circle. It's not a circle. It's almost a circle. I'll draw one. And don't forget rule, whatever it is, 1, 2, 3, 4, 3 or 4. Wherever the isotherms cross the adiabats in the interior, they must always cross at right angles. Now, if you don't draw good, and maybe you said this line here leaves here and goes out like that. And I say, gee, that's not a right angle. I'll believe you if you do this. Okay? So help me give you partial credit by doing things like that. I know people aren't the best sketchers in the world, but at least show me it should be at a right angle so I know what your thought is there, okay? And then I'll believe you. Okay. So here we go again. All right, that's one. Let's draw another one. And another one. Notice everywhere, these guys cross at right angles, or they should cross at right angles. They're not a bunch of concentric circles, no. They're all crammed up near the top, and they've spread out at the bottom. Now that is how you draw a heat flux plot. Label them, isotherms, adiabat. Show the boundary conditions. Show what happens in the middle of the object. Okay. All right. Just want to go over that so you know how it should look when you're done. Okay. All right. We'll see you then on Friday. We've got homework due on Friday, chapter 5.